Hi, everyone. I hope you're having a good, vast conference. I'm here today to present some semi-tested lessons. As we all are facing COVID, things are not quite working out as we planned, but I have three wonderful students who are in our MT program at VCU who have a chemistry focus. And so we've chosen to do some lessons using some green chemistry ideas. And I'll let them each introduce themselves. Elizabeth, why don't you start?
Hello, my name is Elizabeth Miller, and I got my bachelor's degree at VCU studying chemistry, and I really enjoyed chemistry in high school and in college, so I decided that I would like to continue to teach high school chemistry. So then I applied to the master program and got the Noyce scholarship. So I decided to become a high school chemistry teacher, and this will be ready to teach next year.
Julia?
Hi, I'm Julia Byro. I'm currently an MT like everyone else. I went to JMU for my undergrad in chemistry. I taught for a few years for a couple different nonprofits here in the city of Richmond doing education work, and that cemented my desire to want to teach, so now I'm fulfilling that dream. Thanks for having us.
And Andrew.
Hi, I'm Andrew Liang, and I'm also an MT at VCU, preparing to become a chemistry teacher. And currently, I'm teaching in Henrico County at Hermitage High School, and at the same time taking classes here and learning how to become a better teacher. So it's good to be here.
And Andrew went to UVA. So we have a diverse group this year. And they all are Noyce. Andrew is also what we call a RTR. He's part of our residency model. So he has support from two different projects. But the Noyce project at VCU is a scholarship program that's funded by the National Science Foundation. The goal of Noyce is to encourage talented science, engineering, math folks to come into the profession and become mathematics and science teachers. VCU is in their third phase, and we recruit both science and mathematics students. Being in our third phase means that we're at about year 12 of being able, the 12th year, being able to fund students and help them through their master's program. Once they get finished the master's, they'll have their license, and then we have an induction program for them, and we support them for 2 years. And if you're interested, please don't hesitate to contact us. We also have many Noyce projects going on around the state. So you'll see them at several of the universities. Some are as old as mine, and some are brand new. And so it's really great that we're able to offer these scholarships to so many students. As I mentioned, we decided that we were really interested in taking a green chemistry bend to our session. I think what you'll see is that a couple of the lessons are really chemistry focused, but when you get to the fourth one, which is mine, it's not just chemistry. It could be used in environmental science. It could be used in biology. It's really all about how do we do chemistry or use chemical sorts of ideas in a way that is better for the environment, more economical, and maybe even outperforms what we've been currently using. One of the websites that we found very helpful on getting started with this is listed here. In the bit.ly folder, there is also a document with other resources that you might find interesting. So we hope you'll look at that. So for those of you that are not familiar with green chemistry, there's basically 12 principles of green chemistry. Everything from waste prevention to trying to develop safer chemicals to using chemicals in different ways, and then trying to do things more safely so that we prevent any accidents that may have been a problem with a process or procedure in the past. So what we're going to do is each of us is going to present a lesson, and we'll also highlight for you, some of the principles that you could highlight with your students as you're working on the lesson in our near future. Hopefully, when we're all back face to face and it's a little easier to do some chemistry labs. So I'm going to turn it over next to Elizabeth.
Hi, everybody. It's me, Elizabeth. I am going to share the lesson with you that I found to just highlight inquiry and green chemistry. The purpose of this lesson is to note that green chemistry doesn't really have to be limited to just one type of lesson by itself. Instead, it can sort of be incorporated into other lessons that you can teach throughout the year. So those green chemistry principles that we saw on the previous slide, different ones of those can be highlighted. And the ones that I chose was waste prevention, and then just practicing safer chemistry in general, and then designing safer chemicals as products as the result of whatever procedure that you're doing. So what we are going to examine right now is a safer version of the flame test. So a lot of teachers are familiar with this, the flame test for electronic transitions. This is especially popular when introducing atomic theory. I have seen this used as both a demonstration and a lab that the students can do to get them to talk about the different colors that metals burn based on their electronic configuration. So traditional labs, they use nitric salts, sodium nitrate or calcium nitrate. I know that in Chesterfield County Public Schools, these chemicals are actually prohibited so that students cannot use them. But the alternative option that I propose in this lab, they use acetate salts. And these chemicals, they are not prohibited for students to use. So the students can actually conduct the investigation themselves. So this also makes it environmentally benign and functionally equivalent, if not surpassing what the normal version of the lesson would be. So that's definitely an advantage of this lesson. And as some of you, I'm sure, know, nitric salts are harder to dispose of. They are oxidizers, and they can contaminate the water if you don't sort of get rid of them correctly. So again, this lab would end up being more eco-friendly if we were to use the acetate salts because the byproducts are less harmful. So again, this lesson, it's not specifically devoted to the study of green chemistry, but the topic can be discussed with students if we are mindful of the environmental impact of chemistry practices, and that should be integrated into as many unit discussions as possible. It's a similar thing that we consider when we talk about introducing the nature of science tenets and then talking about safety. Those kinds of things are brought up throughout the year as we remind students of why they're important. So, and again, this green alternative, it's a safer option for students, so it provides more opportunities for inquiry learning. And inquiry is a way to involve students in active learning, and it doesn't always have to be high-tech or involve complicated materials. So this is a link to a video that will show you how the flame test works and what it looks like. Because of the situation, I was not personally able to. So I hope that video was interesting to see. I also like how he talked about the street lamps. So again, he engaged the students in just like personal lives, seeing where the color change affects different things that students are used to. So that can just show you what it would look like to actually use it in the classroom. So now we're going to talk more about the 5 E's of the inquiry lesson. It starts with engage at the top of this circle, and then explore, explain, elaborate, and then evaluating, which really can be done throughout
the entire process. I have this online resource where I found the lab initially, and then I included the adapted lesson plan, which is also in the bit.ly at the beginning of this presentation. Again, this green chemistry lab, it makes the inquiry more safer. And you can really, again, still tweak it yourself if you would like to by varying the ways in which you do these 5 E's and the amount of control that you put in the student's hands. So originally, this lab was structured as an inquiry, a structured inquiry lesson, where the question about asking students what causes the flame color to be different, that was provided to students, as well as the procedure by which to do the investigation. And then students would end up determining the answer to the question themselves. So that's, again, that's structured, but then I reformatted this lab to be more of a guided inquiry lesson. And in this design, the question to investigate is still given, but the procedure used to answer the question is more left up for the student to design. And then they are initially going to be testing their hypothesis through an investigation about what causes the colors to be different. So I took the lesson plan and I showed these 5 E's in this chart to kind of just make it clearer. What leads this lesson is the essential question: what causes the flame colors to be different? I think another great part to using the 5E model and using the essential questions is that you can sort of go further out with the scope of designing these essential questions. If you were to look at the entire unit on the atom and not just this one lesson about electron configuration, you could take this same essential question about what makes atoms different. You could frame it that way and then touch base to that essential question while you're going through this lab, so that students will be able to connect these different topics all together. But for this specific lesson, in order to just stay within the parameters of the lesson I made, I just stuck with this essential question: what causes the flame colors to be different? So you have the 5 E's. To start with, engage. I have a fireworks video, which I included the link for as well. And that sort of just get students to be interested in the topic and think about, oh yeah, why do fireworks have different colors? Why should I not be able to answer that if I'm in chemistry? I should know that. And then with that, you could take that discussion and sort of go into the essential question, propose this, the question that you investigate in the lab, and then you explore. So this is where you put some of the learning in the students' hands. You list the materials that you have, the acetate salts, and then you facilitate the students to design the experiment. And then you can put their design into practice through this green chemistry lab procedure. So ways that you could sort of support students in doing this is you can ask, what variables would you like to change? What variables must you hold constant? What kind of data would you like to collect? What are you going to be looking for? What kind of observations are you going to take? And then how are you going to record that data and report it and evaluate it? How many trials should you run? Ask them to identify their independent, dependent variables, and then use an if-then statement to create a hypothesis. So, and another idea is to sort of do this in at least 2 days, to explore and engage the first day and have them design the lab, and then continue the exploration in the second day. And then that will give you a time to take their ideas from the planning and then to put that into the procedure that I'm giving you from this lesson. So it's a way to put them in control while still monitoring it. And then you have the explain section, which is when students are explaining what they see in the lab. And then it's also you explaining some important vocabulary terms and giving explanations about what's going on. So here is a good place where you can sort of take some misconceptions and correct them. And then elaborate is a bigger picture. Instead of just talking about what you see at the lab, you're elaborating further on the discussion and you're making connections between what other students say. They can consider each other's perspectives. They can consider how they learned what they originally thought at the engage stage and then what they learned after the explanation phase. And they can continue to evaluate their original hypothesis. And then you could even make connections between other lessons and other topics to relate this to atomic structure. And then evaluate, again, it's a lot of freedom in what you choose to do, notebook entries, data reports, anything that's a formative assessment. You could even do a summative assessment if you were wanting to do that. And then I pulled some standards that this lesson would help you meet just to get you to desire to do this lesson. I know that if some teachers are probably on the fence about focusing on green chemistry because there are a lot of other things to consider in lesson planning, and a lot of it is hitting these standards and just getting your students ready to take the test that they need to take. But this is a good lesson to sort of get your feet wet, to try out integrating green chemistry principles into your lessons before you have the freedom to really focus on it as a whole topic. So again, there's some Chemistry 1 standards, which is in most lab procedures, and then Chemistry 2 standards. And then these are the learning objectives that I sort of created. And you'll notice that some of the verbs, describe, define, predict, form, plan, those are higher level thinking actions that the student would need to take, as opposed to just normal learning objectives that might say student will understand. And this way, you can form for yourself a way to measure their understanding. If they are correctly describing something, if they are predicting the behavior of different cations and the colors that they'll have, and they base that off of the electron configuration, and they link that to the structure of the atom. And then another thing to point out is how this will be such an engaging lesson that you can touch base with this lesson continually. So as you go on with the Chemistry 3 standards and you talk about bonding and ionic and covalent bonds, you can sort of link it back to this lesson and say, well, what about, those acetate salts? Do you think that's ionic? Do you think that's covalent? And then sort of get them to just connect all of the dots of how this science, the chemistry, how it all connects together. And then this is the lab procedure. Again, it is easier and safer to implement. These steps are very simple, and again, they're tweakable. So if your student wants to look at different compounds, you could sort of make a different way to do that. If they want more trials, if they want to do more research, you can definitely integrate that into this lab. And that's another thing that you can bring up. If they suggest compounds that are unsafe or not usable, you can connect that to green chemistry. And you can say, well, we can't use barium because it'll be more dangerous. And you can sort of talk about those 12 principles at the beginning and link them into the student's decision-making process. But from these results that I included, the student will be able to see the difference between these two compounds where they both have sodium, one has acetate, one has chloride, and they're different colors. And then these two, because potassium and sodium are different, they have different colors, same color here. So that will lead them to the correct answer at the end of the lab. And then these are the reflection questions that also came with the lab. I think that this is a great way to connect inquiry experience to content subject, and then have the green chemistry practices just reflected on. Especially in question number 5, when it asks, this is basically the question that I had just talked about, but if it doesn't come up when the students are planning, then you can talk about it here again. And then again, number 1, will definitely hit the learning objectives of, explaining why and making connections about what's going on. And then the next one talking about making predictions based on these different chemicals. It'll just be very engaging. And then I included a URL link at the bottom. These are further test questions. They are specifically on green chemistry as a practice. It's from the ACS. And you can integrate that into quizzes and tests when you're talking about the atomic structure. You can sort of remind students of the importance of green chemistry. And then these are additional resources that I have from the ACS as well. These are both about fireworks. So you can use these to sort of do a full circle with the lesson, and you can have students learn more about how they work and why the colors are different again in this video and then this reading. So I hope that that is enjoyable, and I hope that this is a lesson that you will look further into and hopefully implement into your classroom, because I think your students will really enjoy it. So thank you so much for listening to me, and if you have any questions, you can always ask Dr. Edmondson. Thank you so much.
Hello everyone. Again, my name is Julia Byro, and today I'm also presenting on a lab from Beyond Benign Green Chemistry Education. On their website, this lab is called Writing the Principles, but for a little bit of clarity, I've retitled it Student-Generated Green Principles, because how this lab works is students are given a procedure that has too many steps, it produces waste, it's tedious, and the goal is for students to get frustrated to the point where they realize that they could redesign this lab to be more efficient and less wasteful. And in the process of them redesigning this lab, they will more than likely hit on a couple of the principles of green chemistry without even having learned those principles. You can find the original lab procedure down at the link below, and you can find a link to my lesson plan in our bit.ly that Dr. Edmondson introduced at the beginning of our presentation. So in this lab, students are tasked with making casein glue, which is a milk protein. This is a great lab to do at the beginning of the year, especially if you want to introduce students to lab work in your classroom early on. You can introduce them to safety during this lab. You can introduce them to skills like measuring or dimensional analysis. Another good thing about this lab is you don't really need any prior scientific knowledge, so you don't have to do a lot of background teaching before students can get really hands-on. You can refer back to this lab throughout the year, not only because it hits on a lot of principles of green chemistry, but because it hits on a lot of things that are included in the nature of science tenets. And in general, it's just a fun lab because students get to be hands-on, they're making something sticky and weird, and it's just really engaging from the beginning. So the procedure is really important to this lab, so I wanted to give you guys a brief overview of it. Students are asked to measure out a certain amount of milk and then immediately discard half of it. After they get their milk, they are asked to put 4 slices of canned beets into their milk, mix it with a plastic spoon, and then discard the remainder of the beets and the plastic spoon. After that, students are asked to put vinegar into a centrifuge tube and then place the centrifuge tube into a fume hood for 20 seconds. While their centrifuge tube is in the fume hood, they're heating their milk up to 45 degrees Celsius, and then they mix their vinegar in to their milk, their heated milk, and that will produce this solid, which they then decant while their lab partner says the ABCs backwards. They then wash the solid that they get with an alcohol wipe. Once they've rinsed any excess vinegar off of their solid, they mix their solid with a little bit of baking soda and naturally glitter. Then they add an excess amount of water and wait for that water to evaporate until they've got the right consistency for an effective adhesive. So already we can see there's way too many steps, and students should pick up on this pretty quickly. So here I've outlined some potential student modifications that they would likely come up with and how those modifications relate to the principles of green chemistry. So for example, that first step, when students measure out more milk than they need, eliminating that relates to the first principle of green chemistry, which is to prevent waste in the first place. They could also reduce the number of steps overall, but make an equally effective glue. They might take out the beat step because the beats are really just there for color. They might take out the glitter. In doing so, they will still have just as effective of a glue, but with fewer steps. And so that relates to principle number 4, that design choices preserve efficacy of function while reducing toxicity. We also have the option for students to use a glass stirring rod instead of a plastic spoon. And this relates to principle number 7, the use of renewable feedstocks. And then principle number 9 is about catalysts and using catalysts whenever possible instead of a stoichiometric reagent. Vinegar in this lab is a catalyst, but in the lab procedure, they are asked to discard of the vinegar after they use it. So if students do come up on their own with the idea to recover the vinegar, then they would also be hitting on another principle of green chemistry there. So I've taken this lab and put it into a 5E model. The first step, engage, of course. You can start by telling students that they are material scientists, and their goal is to make an effective adhesive. You can provide students with a little bit of background, and there's lots of great videos on YouTube about what material science do, what their goals are, and what the methods they use are. I've included one in my lesson plan. It's a really good crash course video that is short, but gets to the point pretty quickly. In the explore phase, students will be actually doing the experiment. In this process, they will likely say, why are we throwing these away? Why are there so many steps? And they might be getting frustrated. And the goal is not to try to trick them into thinking that this is what science is actually like. So the teacher should sympathize with those feelings. The lab procedure says try to get through to the end of the procedure, but if students get to the point where like, this just doesn't make any sense, then it's perfectly fine to stop there and then have students start redesigning. And in the explain phase, you explain why students went through that process after that first round of the lab, and explain that it's up to them to redesign the lab to make it more efficient. In the elaboration phase, you can outline all of the ways that the student redesigns mirror the principles of green chemistry. So you're making that connection for them. I would take a couple of examples just to illustrate your point, but I wouldn't do all of the work for the kids. And I'll explain that more a little bit later. I would also, in the elaborate phase, provide examples of how green chemistry is used around the world, different examples of it. There's another video that I've linked to that describes how ibuprofen actually uses principles of green chemistry, and that's why ibuprofen is so much more affordable today than it was originally. And then in the evaluate phase, I think that a really good way to evaluate how well students are grasping the 12 principles would be if students peer review each other's work. They can identify which principles of green chemistry their peers used in their lab redesigns, and they can also add their own suggestions because they've gone through the same process. Now, the only standard in the Virginia SOLs that this lab really hits on is the first standard, which is to demonstrate an understanding of scientific and engineering practices. Because students are planning their own investigation and carrying it out themselves, they're also asking questions and defining problems. But this also hits on a lot of the tenets of nature, the nature of science, like I said before. And those include that science is both reliable and tentative. So students are given a process and they realize themselves that, hey, this could be improved upon. And you can tie that to a number of historical examples. It doesn't mean that science is not reliable because they had to change a process. It actually makes it more robust because the scientific community comes together and makes things more efficient. Another one that it hits on is that scientific knowledge is a product of creative thinking. Students have to be creative, and so do chemists who take on the principles of green chemistry. Science is a social activity that possesses inherent subjectivity. So you could explain to students that maybe a certain process isn't totally green because of the kind of funding sources that scientists have. Maybe they are being pressured into using a certain reagent that is toxic, that will lead to byproducts that are wasteful. And so learning objectives for this lab are that students will be able to explain how wasteful processes are bad for the environment. They will be able to refine a procedure to make it more efficient. They can identify the relationships between the work that they're doing and the work of real scientists, even though they are real scientists. And they can describe how their peers' modifications relate to the principles of green chemistry explicitly. There are some additional resources I've included here. Of course, the lesson plan is in our bit.ly folder. And VCU School actually has a great series on each individual principle of green chemistry, which I've also included in my lesson plan. Thank you for the time, and I'll pass it off to Andrew now.
Hello, everyone. My name is Andrew Liang. I'm a chemistry teacher, first-year chemistry teacher at Hermitage High School in Henrico County, Virginia. This is my submission to the VAST conference, continuing on the theme of green chemistry. My submission is about renewable energy and carbon capture and storage. The lesson is broken down into a few labs, 3 labs in particular. The first one is generating renewable biofuel. This is a simple ethanol fermentation, fermenting sugar into ethanol. And the concepts covered are the basis of renewable energy, its viability and cost and principles, and catalysis, because the yeast used to generate ethanol from the sugar, the glucose solution, participates in the reaction but doesn't get consumed. The second lab is one method of carbon capture, which is a post-combustion capture, meaning when factories and power plants produce smoke that gets released into the atmosphere. This is a way of capturing it at the source, basically filtering and capturing the flue gas that is emitted before it can be spread into the atmosphere. This is done with amines, and the concepts covered are gas stoichiometry, because students can calculate the volume of gas produced in all the reactions, and use of basic lab equipment, because this lab will require a graduated cylinder and among other pieces of lab equipment. The third lab is another method of carbon capture, which is called direct air capture. This is if the gases and the CO2 have been already released in the atmosphere and we want to remove it from the air directly. And concepts covered are air filtering and phase changes, because we want to collect the CO2 and eventually it will change to either a solid form as calcium carbonate or as a liquid. There's no liquid form, only gas form, and only solid form. Yep. So 3 labs here, each a unique way of capturing carbon, whether it's at the start when you prevent it, while it's being emitted from the factory, and if it's already left the factory and been dispersed into the atmosphere. So the first lab, prevention is the best cure. So it's more expensive to retrieve a ton of CO2 from the atmosphere than it is to prevent it from being released in the first place. Okay, so this is why we use renewable energy to reduce our net carbon emissions. And a very introductory example that many students can understand is the use of ethanol, which can be burnt as fuel, and it can be generated very simply. We have a sugar solution, we add yeast, and ethanol and CO2 are produced. Here's a video link showing the process, and the students can watch the reaction take place because they're watching the bubbling going on as the yeast is consuming the sugar, converting it into ethanol, and the CO2 release is being captured in a balloon that is attached to the top of the bottle. All right, but then the problem arises. What do you do with that captured CO2? If we were a factory generating ethanol as a biofuel, we would still be producing CO2, and how can we dispose of it? That brings us to our next carbon capture method. Capturing at the source. So here, maybe we can take our CO2 generated, we can react it with an amine, which reacts to produce a carbamide, and this then can react with heat and acid to release the carbon dioxide. So if the school has access to a flue gas source, then this would make a lot more sense because it's not only CO2 being reacted and captured, but many pollutants, and then this isolates the CO2. And the CO2 captured can be bubbled into a solution in an inverted graduated cylinder, which shows the volume of gas produced. This covers gas stoichiometry, and the video links describing these two experiments, which I've combined into one, can be found here. Lastly, if we fail to capture CO2 from the factory, we fail to use renewables, and it's already in the atmosphere. Here's a way that we can capture it and remove it from the air. This is still a prototype. It's still a work in progress, but the proof of concept can be demonstrated in class. So here it is. CO2 can react with potassium hydroxide to produce water and potassium carbonate. And the way we do this is we have a sploof or a paper towel roll covered with a paper towel, and inside are the reactants. So we can have potassium hydroxide, we can also have calcium hydroxide. And by exhaling through it, the CO2 passes through and reacts, and the goal is to generate calcium carbonate as a product. Direct air capture through this method turns CO2 gas into solid CO2 pellets, condensed, easy to dispose of, and can be reused actually. It can be used in soda, or taking this process further, it can be reconverted into hydrocarbon. So the product, this doesn't have to be done in the lab, but just to illustrate how we can achieve a carbon neutral process, we can take carbon dioxide from the air and convert it back into fuel. So an important aspect of this is that students do their own research into these methods. They want to look into the cost, the viability, the efficacy, and the timeline if we were to implement this. And what do we do with the stored CO2? Do we just deposit it underground in the ocean? Probably not the ocean because of ocean acidification. Outer space, anything's possible. They'll have to evaluate what can be done. This is a very open-ended kind of inquiry. And another issue to address is whether CSS technology can adequately combat climate change on its own. And a lot of climate scientists will tell you, no, it's not enough to just do CSS. It's part of a broader strategy to address climate change. Here's another method in their research. They may come across new methods of carbon capture, one being converting CO2 gas into a solid to get dry ice using like liquid nitrogen and store it in Antarctica. So just to illustrate how many directions this can take and the flexibility of it. Here's a quick breakdown of the lesson. Start out by capturing their attention and discussing the threat of climate change. This introductory video, which is real short, less than 4 minutes, by Bill Nye. Then have students go on their own and do some research. Evaluate the available methods for carbon capture, renewable energy, and that'll give them ideas. So when they finally do their experiments, they'll have a conceptual basis of what they're doing. They'll perform these 3 experiments. They can be put into stations, or one can be done in one day, the other can be done another, or just any of them can be taken out and done individually. They'll discuss the results, especially the chemical principles. The teacher will have to guide them through catalysis, gas stoichiometry, and phase changes. And lastly, perhaps the students could write a report or a proposal describing their findings, evaluating the viability and capability of these different methods. Here are the SLs addressed: planning and carrying out investigations, independent research, gas laws, phase changes, and here are the learning objectives. So thank you for listening to my proposal, and hope there's a good conference. And if any questions need to be asked, feel free to contact me or reach Elizabeth Edmondson at VCU. All right, thank you very much. Have a great day.
Hi, everybody. It's Elizabeth again. As I began thinking about green chemistry and the winter coming, I thought it would be really interesting to do something with de-icing compounds. We see lots of things being spread on roads and sidewalks, and we might not think too much, or at least our students might not think too much about what some of those materials are. So in thinking about a lesson, I drew from several resources. In our Bitly folder, you will find a lab that you can actually purchase from Flynn, but I sort of figured this out playing with some ideas myself, and wanting to be 5Es and green, I started with these pictures. And so as an engage, you might start your students by having them look at these pictures and think about, what do they have in common? What questions do they have? How are they different? What might be going on with this? And then I would get them into explore, which in this case I decided would be a guided inquiry into how different de-icing chemicals impact plant growth, ultimately so that we could figure out which of these would be best to recommend for using on roads and sidewalks. So being guided inquiry, I've given them the investigation question. They would have the opportunity to think about the different variables, what they're going to control. I set this experiment up, and we're going to look at the results here in just a minute. One of the things I want to emphasize is the need for safety. So please don't forget about trying to stay safe with the materials. I used, in this case, lettuce seeds, and they worked quite well, but you could use radish. We used a variety of chemicals. Yes, a data table for them to record their observations. You'll see I had water as the control, sodium chloride, magnesium chloride, calcium chloride, and beet juice. But you could also, instead of beet juice, you could use red cabbage juice, and that is used sometimes as well. I made saturated solutions for each of these to use in the investigation. So on day 1, I set these Petri dishes up, so day 0, with 25 seeds, which was interesting to count because they were tiny, and put them in each of the solutions in one day. I know it's a little bit hard to see, but after one day, the ones in water had already sprouted. The others had not. And here's the results after 7 days. The only ones that sprouted were those that were in the water. None of them sprouted in any of the other solutions. So then you could spend some time with data analysis and move into your explain and have students think about what they observed. You might want to do some short teaching or reviewing on ideas like osmosis, diffusion, process of germination. But ultimately, I'd like for the students to create a scientific explanation using the information you've shared with them. And then there's some readings that are included in this as well, so that they can gather some information from various sources. I also believe it's really important for them to share their explanations, possibly do some revisions, and really think deeply about this. and think about how using safer chemicals might help us with being a more green chemistry. So one of the things that's become quite evident to me is that green chemistry cuts across all of the sciences and can be an easy idea for us to use in our classes and think about how to be more environmentally friendly. We hope you've enjoyed